We have a bending member with a rectangular cross-section which is made of ABS plastic. We want to know what is the largest true thickness edge crack length, A, that can be allowed if the moment is 12.5 Newton meters, and B, if the moment is 3.0 Newton meters. And we will consider a safety factor against brittle fracture of 3.5. Finally, in part C, our goal is to determine the safety factors against fully plastic yielding for case A and B. We know that the critical stress intensity factor over the safety factor will be equal to form factor times S gross times square root of pi times the crack length. And for this shape, for alpha smaller than or equal to 0.4, we can use the form factor as 1.12. We also know that S gross will be equal to 6m over b squared times d. From table 8.2, we get the critical stress intensity factor as 3 MPa square root of meters. And considering this equation, we also know that the critical crack size will be 1 over pi times the critical stress intensity factor over safety factor times the form factor times S gross square. Now let's start with the part A. For m is equal to 12.5 kilonewton meters, Sg will be 6 times 12.5 kilonewton meters over 24 millimeters square over 8 millimeters, and this will be 16.276 MPa. Let's assume alpha is equal to AC over B. It will be smaller or equal to 0.4, so that F is equal to 1.12. So when we calculate AC with this assumption, we will get AC is equal to 0.7037 millimeters. But first we should check if alpha is smaller than 0.4. This value satisfies our requirements, so we can take this value as the crack length. So let's move to part B. For m is equal to 3 Newton meters. The first one is also Newton meters, I am sorry. Okay. Sg will be and it will give 3.91 MPa. Again, we are going to assume that alpha is smaller or equal to 0.4. But when we make the computation, we will see that AC will be 12.19 millimeters. And alpha, which is equal to 12.19 over 24, will be bigger than 0.4. So we won't be able to use this assumption, and we should solve AC is equal to 1 over form factor square, and we know that's the function of alpha, times the rest of the equation, which is equal to 0.015 297 meters. From figure 8.12, we got a form factor equation as and this is 23. Okay, so when we calculate this, we will obtain AC is equal to 9.8 millimeters. Now we can move to part C. We know that the safety factor against yielding will be the yielding moment over the applied moment. And we know that the yielding moment is equal to yielding strength times B squared times T over 4 times 1 minus alpha square. This is from figure 8.16, part B. And from table 3.3, we see that the yield strength for our material is between 34 and 50 MPa. We can take the average and make the calculations considering this yield strength. For our case in A, the yielding moment will be equal to and this will give 45.59 Newton meters. Thus, our safety factor will be 45.59 over 12.5, which is 3.65. And for our case in the part B, bending moment will be equal to and this equation will give the bending moment as 16.94 Newton meters, and this will give a safety factor of 5.65.